Okay, here we're going to look at the 0.2 Algebra 2 review packet. Credit goes to Miss Gelly for creating this packet. I'm using it because I think it's a great packet. It has some awesome review in it, but shout out to her for making the packet. All right, so starting out here, we have a graph. We're looking at analyzing a function. It says given the function f of x to the right, so here's f of x, we're going to look for a bunch of features. And f of x doesn't appear to be any of the main functions we studied in Algebra 2, but that's fine because we can see the domain appears to be all real numbers. You could state like this. You could state using inequalities, or you could state it using interval notation. So I recommend being comfortable with all three, but you can kind of pick whatever way you like. One thing I do want to note is it appears that this function has an asymptote along the line y equals 0. And so we're going to assume that that is in fact the case. All right, therefore the range of the function appears to go from that asymptote 0, so not inclusive, all the way to 10, which is included because we do reach this point 10 on our graph. So that's interval or inequality notation. If we want to show it with interval notation, I would do curly bracket 0, meaning 0 not inclusive because we never get there, and 10 with the square bracket to say 10 is inclusive. X-intercepts, well, based on our graph and that asymptote, we would say that there are none. Y-intercept, we would say is at 0, 10. Extreme values, so these usually refer to any maximums, minimums of our graph. So we could talk about if we had some polynomial, maybe all these maxes and mins. So on our graph, that just tends to be the maximum. We have a max at 0, 10. It is an absolute max or a global max at 0, 10. And we do not have a minimum value because we keep approaching 0, but we never actually get there. And there's nothing else that would be an extreme value. Increasing interval. So where is this function increasing as we read it left to right? Well, we are increasing as we go this way, and we are decreasing on the way down. So we increase all the way to the max, decrease all the way down the function. So we're increasing from -infinity to 0 because this the intervals are always really typically described based on x. Based on x. Okay, so with interval notation, -infinity to 0. Now I say it's not increasing at that point 0. If you were to put this inclusive bracket, I think that's fine too. Or if we wanted inequality, well, yeah, we probably wouldn't want inequality notation. I like interval notation for this. Okay, the decreasing interval then is from 0 to +infinity, so we will always be decreasing from that maximum point down on to infinity. Our end behavior, again, that's going to be based on x. So we're going to say as x goes to +infinity, f of x is going to approach but never reach 0. So we say f of x is going to 0. As x goes off in the -infinity direction, f of x is also going to 0. Describe the symmetry of the function. So this is an interesting question. The symmetry, if we look at the function, it appears to be symmetrical over the y-axis. Okay, and that's sufficient for describing it at this moment. Technically, this is called even symmetry, or it is an even function. That's not something you should worry about at this moment. Maybe you've seen that before, probably not. We'll cover that a little bit later in this packet. It gives some direct instruction on that. But for now, symmetrical over the y-axis is all you'd want to really think about. Then if we want to evaluate the function, well, we don't have an equation for this function, probably not going to figure one out. So let's clear some space. And we just want to evaluate. So that means when x is -1, what's our y? So if we look, it appears to be 5. So f of -1 seems to equal 5. F of 0, well, we said that's our y-intercept. F of 0 is 10. Let's see. F of 2 input of 2 seems to give us an output of 2. Solve or estimate. So now we're given f of x equals 5. So this is like when or is y 5. And by when, we mean for what x value. So let's say that. For what value of x is y, or f of x, or the output, 5. So if we look at that, if we go to our graph and we sort of look at where is y equal 5, we can see that it's 5 at this point, negative 1 comma 5, or our graph would be 5 at the point 1 comma 5. That has to do with this even symmetry. We're symmetrical over the y-axis, so we should have these sort of corresponding positive and negative copies. So we would say at x equals 1 or x equals negative 1. When is f of x 8? So this one's going to be something we have to estimate. Without the equation of this curve, well, f of x equals 8 is like here and here. If we estimate down, I mean, maybe you could argue that that's a half. I think that's a little less. I might say like 0.3 or 0.4 for x. Little bit tough to sell. I'm going to say 0.4. So we're going to say x equals 0.4, and based on symmetry, x equals negative 0.4. Maybe your eyes are better than mine, and you can zoom in and say, oh no, it's 0.5, Mr. Miller. But I don't know. I'm putting at 0.4. Sue me. Just kidding. All right, f of x equals negative 2. Well, if we look at this negative 2 line here, yeah, we're not going to get there. This function has an asymptote at y equals 0, so never. Okay, there's no x value that makes that true. So there we go, first page, analyzing functions. We looked at all their behavior, practiced a little notation, evaluating, and reading graphs. So we're going to get another opportunity to do that on page number 2. So you've given the function g of x to the right, state the domain, range, blah, blah, blah. This one, I think, I mean, you could check it in Desmos. My thinking is the equation for this function is actually g of x is equal to the square root of 25 minus x squared. That might seem a little random, but it's a semicircle with a radius of 5, and I just happen to know that sort of gives you the positive semicircle with a certain radius. Looking a little different, I mean, that 25 is 5 squared, right? So again, you're not expected to know that, but I do, so I'll put it down and we can think about that. Domain. So the domain is not all real numbers. We can input from negative 5 to positive 5, and it is inclusive. So we need these square brackets, or you could say negative 5 less than equal to x, or x is greater than equal to negative 5 less than equal to 5. Which checks out with that function above, right? That 5 and negative 5, when we square it, we get 25, we get square root of 0, which is kind of our cutoff, because when you start taking square roots of negatives, you end up with imaginaries, which don't show up on this 2D graph. Range of the function looks to be 0 to 5. Again, both inclusive. We can get out 0. We can also get out 5. And that all checks out with the g of x I wrote. Inequality, we could say y is greater than or equal to 0, less than or equal to 5. X-intercepts, we do have those coordinates as x-intercepts, so we have negative 5 comma 0, and we also have 5 comma 0. Y-intercept, we have 0, 5. That's it. Extreme values. We'll take, I mean, obviously we have this max here at the x-intercept, so we have a max, and it's an absolute max. I said global max before. They're also called absolute max. So I'll mix and match vocabulary just so you see both versions. That's 0, 5. For this function, I mean, we do have these minimums, right? Typically, I prefer when there's like a nice curve there that you get the max of, but I don't know. We'll call those the minimums. So we would say absolute mins at negative 5 comma 0 and 5 comma 0. And I don't know. I don't know what your calculus teacher would say if those both count as mins and if they count as absolute if there's two of them. But whatever, the point is for you to realize that that's the minimum value of the graph, right? For right now, that's all that you need to worry about. Determine the increasing intervals. So again, as we move from left to right, like here we're going up, 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 right? We are increasing to our maximum, and then we go left to right, down, 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 down. We are decreasing from our max to our other min. So our increasing interval is from that -5 all the way to 0, because again, remember that refers to the, put this in orange, x interval. And I'm personally of the opinion that at -5 and 0, we are neither increasing or decreasing. Yeah, but if you included it, that's fine. I don't know, I've seen it done both ways. And then the decreasing interval, we are going to say from 0 to +5. Depending on, well, whatever, that's all I'll say. And that was the decreasing, sorry. Zoop. End behavior. So we don't have end behavior off to infinity. We have end behavior where x approaches 5, f of x is going to 0. And as x goes to -5, f of x is also going to 0. So that's just saying on both ends of our function, the outputs are going to 0. One of those ends is when x is approaching 5 or gets to 5, we get 0. When it goes to -5, we get 0. Symmetry. Again, we've got this beautiful symmetry across the y-axis. And again, I mean, this is called even symmetry, or an even function. You don't need to know that until a little later in this packet. You'll get full-on instruction in that. But yeah, it basically just means symmetric over the y-axis. All right, let's get evaluating. So g of -1. So I've got this function up here, but let's just use our graph anyways. So g of -1, well, that's going to give us something a little bit less than 5. Call it 4.9. I think it should be, if we actually plugged in -1, we would get the square root of 24, which I'm just going to cheat and put in a calculator, which is 4.8989, blah, blah, blah. So 4.9 is a pretty good estimate. So we're going to say 4.9. G of 0, we seem to get this integer coordinate of 5. G of 4, if we shoot this 4 up, we get 3. That's pretty nice. And that's not a coincidence. Here we have a 3, 4, 5 right triangle, right? This is a semicircle with radius 5. If the x-coordinate is 4 and the radius or the hypotenuse is 5, well, then the y-coordinate has to be 3. So that's kind of neat. And then g of 6, well, we don't get anything, so it's undefined. It's not in our domain. Okay, g of x equals 8. Again, g of x equals 8 would be way up here. Our function just doesn't get up there, so we are undefined up there. G of x equals 3. So go a little yellow. My graph's getting messy. G of x equals 3 is here, right? So we said one of those was when x is 4. The other is when x is -4. So we have two possible answers. X equals 4, x equals -4. When does g of x equal 0? Well, that is when our function is, let me erase this yellow, clear up a little space. Here we go. G of x equals 0. So that's really when do we cross the x-axis where our x-intercepts, and those are at 5 and -5. So we can say at x equal 5 and x equal -5. Which you could write like this, x equal 5 comma -5. That's saying it's both 5 or -5. Whatever you like. Great, so that's number 2, looking at another function. Again, that's not in the family of functions that you studied. It's not really a square root function, like this is a equation of a half circle. Definitely didn't cover that in Algebra 2, but it's good to be able to analyze graphs that you're not always familiar with. Okay, but now we're going to look at some functions that you have studied. So first of all, we note we have a piecewise function, h of x, shown on the graph to the right. And we're told that it's a linear function, so that appears to be right here. a quadratic, which appears to be here, and a square root function. This is nice because without being told that, like technically this could be like x to the power 4 or 6. Like it looks like it could be some even curve. You know, the square root maybe is the 4th root, or maybe it's the cube root in the restrict domain. Like you can't tell what's happening, so it's nice. And we're going to make assumptions that it is sort of these basic versions, but it's nice that we're actually told that. So equation for h of x, we want to write the equation of a piecewise. So we're going to say h of x is equal to, and then we have this little piecewise bracket thing, because we have different domains. So the equation of our line, we have a slope of 1, so that's just x, or 1x. And then our y-intercept, if we continued our line, would be at 7. So it's x plus 7. And that's on our domain from here. And you might wonder, oh, well, does this line continue on? And it certainly doesn't appear like it, because this filled closed point implies that's an endpoint, right? If this was an arrow, then we'd say, oh, that goes on forever. But it seems like our function ends at an input of -10. So we're going to say the domain where it is that linear function is from -10 inclusive to -3 inclusive. Okay. You could also use inequality notation, but I don't know. I like the interval notation. Next up is the quadratic. You'll note the vertex of that quadratic is not on integer coordinates. We have some nice x-intercepts to work with. So let's do the quadratic math over here. So with those x-intercepts, I get x plus 3 and then just x. Those are the zeros of my function coming from -3, 0, and 0, 0, telling me my factors. However, we don't know what our a value is. Right, here's an a value. But we've got some points we can test to solve it. We have this point 1, 6. We also have a point here, -1, -3. And then -2, -3 also. Actually, based on that symmetry, we could get the coordinates of our vertex too, but that's fine. So we'll go a and then equals. I'm going to plug in 1, -6. So here's 1 is my x. +6. 1 +6. So I'm going to get 6 equals a times 3 plus 1 is 4, times 1 is still 4. 6 equals a times 4, or 4a. So a will be 3/2. Meaning, when it's all said and done, let's get this back to green. But that's our quadratic function. If I wanted to test if that were true, which I might, I could test the point -1, -3. So -3 equals 3/2 times -1 plus 3 times -1. So -3 equals 3/2 times 2, cancels, times -1. So -3 equals -3. Great. Beautiful. Okay, so that's our quadratic piece. So if we put that in here, we can say 3/2 times x plus 3 times x. It's a hair weird to write it like that, but that's okay. We don't really have to put it in any specific form. And then our domain. So if we look at our graph, we can see we have this open circle here, meaning that is not included. So we would say -3, and then we're going to go all the way to when x is 1, and that is included by this closed circle up here. Great. Then our last piece of the function, we said this was some square root function. Using transformations, I can say that we are over at 4, 2 for our vertex, meaning we have to be square root of x minus 4 to make it 0 when we plug in +4, and then plus 2 outside. And we're going to need an a value. So if you plug in, say, this point right here, you'd be able to solve for your a value. Another method you could use, if you want to go ahead and plug that point in and solve for a, go ahead and do it. But I know a regular square root function is supposed to go over like this, and then if we go over 1, 2, 3, 4, we're supposed to go up 2, right? So this is what a typical square root function would look like if a is equal to 1. And if we look at our outputs, this is doubled. This is 2 doubled to 4. So I can tell you right now that that a value is 2. And for the sake of showing you, like, all right, here's a coordinate 5, comma 4. If I say 4 is equal to a times square root of 5 minus 4 plus 2, subtract 2, 2 equals a times the square root of 1, or 2 equals a. Look at that, a is in fact 2. So that's all very nice. You can use it either way, but we should end up with 2 square root x minus 4 plus 2. And the domain there is not inclusive. We have an open circle, so we start at 4, curly bracket, and then we're off to infinity. We've got the arrow. Arrows mean we are going forever. Very cool. So our domain of this function, kind of a pain to state. We kind of already stated it in the piecewise function itself. Let's do green. So the domain goes from -10 to -3. Then it also goes to -3, 1, inclusive, and that goes from 4 to infinity. So it's a really choppy domain in some ways, but that's what it is. Okay, range of the function. What a delightful question. So it looks like if we have the square root function, our range is going off to positive infinity. So I'm going to put that down. But the question is, where is our minimum value? If I look here, this is at -10, -3. That vertex is below that. So we kind of have to figure out the coordinates of that vertex, which is a little bit annoying, but we can manage. So using symmetry, here's my function, 3/2 x plus 3 x. That's the quadratic. And I want to know what's the x coordinate of the vertex. And using symmetry, I can say it has to be between -3 and 0. And so between that is -1.5 or -3/2 if you prefer. So if I plug that in for x, that's my x coordinate of the vertex, and I should get out my y coordinate of the vertex. So I'll do this 3, I'm going to turn to 6/2, and then 3/2. So I'm going to get 3/2. This one's negative. Then I'll get another 3/2, and then I'll get -3/2. So multiply that all together, you get -27/8. If we divide that, that would be 3 3/8. If we look at our graph, like that sure looks like -3 3/8. So our range is going to be, I'm going to write it as -27/8. Inclusive, because that is a coordinate of our vertex. And I'll just put that down, -3/2, -27/8. Beautiful. X-intercepts. Okay. So we can see that we have an x-intercept here, -7, 0. We do not have one right here because that's an open circle, not included. But we also do have one at 0, 0. That 0, 0 point also happens to be our y-intercept. Great. Cool. All right, h of -1. So we could use our h of x function to evaluate that, or we can use our graph. I'm just going to use the graph until I can't. So h of -1, plug in -1, we get out -3. Let's keep mixing and matching. Green equals -3. H of 2, we have nothing on h of 2. When we plug in h of 2, there is nothing. The function's not defined there. It's not in its domain. H of 4, also undefined. Even though it is the vertex sort of our square root function, you might note that it's an open circle. So it's not in our domain. If we look at our domain here, the 4 is curly bracketed, meaning it's not included. H of -20. If that was an arrow on here, maybe we would go off there, but we don't. So it is also undefined. H of -3. So plug in -3. That's our x-intercept. That is a open hole, though. That is not part of our domain. For the quadratic, ooh, I almost got caught. However, it is part of the domain. That's tricky. So -3 is part of the domain for the line, not part of the domain for the quadratic. So we need to use the line, and the coordinate when we use the line is 4. So h of -3 is defined, but it's defined as part of that line's domain. So it's 4. H of 1, we said the coordinates 1, 6 are on this graph, so it's 6. H of negative 20 over 3. Okay, what a blast. So negative 20 over 3, if we divide that, that's equivalent to H of negative 6 and 2/3. If we see that, we're going to be somewhere here. We actually need to plug that into our linear function. So I'm going to do negative 20 over 3 plus 7, which is 21 over 3, yields me 1/3. So that equals 1/3. So the way I handled that is I looked to where is this on the line. I could have also said, like, where is it in this domain? And then I have to use the linear function because that's the part of the domain that negative 20 over 3 falls into, so we have to use the function for that part of the domain. Similarly, H of 12, I could look at the graph, or I could just look here. 12 is between 4 and infinity. So we're going to be using the square root function. We don't have the graph to look at. Oh well. So let's plug it in. So we can say 2 times the square root of 12 minus 4 plus 2. So that's 2 square root 8 plus 2. Simplifying our radical, root 8 is 2 root 2, and then 2 times 2 root 2 is 4 root 2 plus 2. So I'm going to leave that as such. Okay, solve or estimate when h of x equals negative 2. Oh boy, would I not quite enjoy solving this, because we're not going to get integer coordinates. So if we look at where h of x is negative 2, we do get integer coordinates from the line. So one place is going to be at x equals negative 9. Right? If I plug in negative 9, negative 9 plus 7 gets me negative 2. That quadratic's got non-integer coordinates. Kind of annoying to solve. Yeah. Ugh, that quadratic's going to be a pain. Okay, well, whatever. Let's hope for the best. So if we do 2 is equal to 3 halves times x plus 3 times x, multiplying by 2/3, we get 4/3 equals x squared plus 3x. 0 equals x squared plus 3x minus 4/3. Okay, in an effort to not have a fraction, it's not a lot of space here. Let's multiply everything by 3. So I'm going to get 0 equals 3x squared plus 9x minus 4. That doesn't factor, which is logical because we have integers. Say at this point, like, go for the quadratic formula. Like, you could complete the square if you want. I have a video on how to program a TI-84 to do the quadratic formula for you. So that's going to be really handy because every time you run into a quadratic like this, it would be kind of nice to just get the solutions without having to go and do all that math by hand. Especially because looking at the answers here, we get some delightful things. So we get negative 9 minus square root of 121 over 6, and we get negative 9 plus square root of 129 over 6. Yeah. I guess I'm missing the fact that the question says to estimate. But the thing is we can solve, so I don't know. Take what you will from it. Whatever's best for your review. Okay, h of x equals 2. I mean, again, when we intersect this line, that's fantastic. Look at how messy my graph is. Should I erase? It's kind of pretty, but it's also a pain. Clear some of this good stuff out. So h of x equals 2. We can see we're undefined here. Don't worry about the square root. Again, we cross at some non-integer coordinate for the x value at the quadratic. And then with the linear, it's super nice, and we get negative 5. So we get x equals negative 5. I don't know. Should we just estimate it? Now let's get the exact answer. So if we say 2 equals 3/2, x plus 3 times x, multiply by 2/3, we get 4/3. Oh, I did the last one wrong. Hope you weren't yelling at your computer. All right, that's negative, 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 positive, positive. So these answers are actually going to be for over here. Off you go. But that means we need some fresh answers for the other one. So we'll put that in the quadratic formula. And we'll see what that yields. Oh, great, something just as pretty. Negative 9 minus square root 33 over 6. Negative 9 plus square root 33 over 6. Okay, so delightful. Just delightful. Okay, I'll finish out the little math over here. So we get equals x squared plus 3x. 0 equals x squared plus 3x minus 4/3. And then 0 equals 3x squared plus 9x minus 4. Just what we had a second ago, multiplying by 3. Okay, h of x equals 3. It's really slowing my progress down here. Are we really going to plug this in and solve to each one? And h of x equals 10. Whatever. H of x equals 3 we're going to estimate. So we're going to say x from the line. H of x equals 3 goes through here, so we can say x equals negative 4. From the quadratic, we'll pretend it's 1/2. So x is approximately equal to 1/2. And then from our square root function, it's a little bit more than 4. Call it 4.25. X is approximately equal to 4.25. So at that point, I decided to just estimate. You could go through the motions and solve it if you want the practice, but there's also just not that much space on this paper or iPad. All right, last one, h of x equals 10. That's only going to apply to the square root function, right? Eventually, that square root's going to come up here and catch that. I'll plug it in and hope for the best. So we get positive 10 equals 2 square root of x minus 4 plus 2, 8. Oh, okay. 8 equals 2 square root of x minus 4. 4 equals square root x minus 4. Square both sides. 16 equals x minus 4. X equals 20. All right, that's nice. Great. Okay, so that wraps up question number 3. And then, yeah, so a lot of practice involved in there. Piecewise functions, domains, and plugging in and solving and using that quadratic formula, which again, I highly recommend. I mean, you can do that thing by hand. You can complete the square. But, I mean, it's going to sort of save you time, energy, and just whatever to have a program in your calculator that just does the quadratic formula for you. So check out my other video on how to program your TI-84 to do a quadratic formula, and that'll put you in good shape. Okay, moving on for our next set of problems, we're going to be using a graphing emulator, which basically just means a graphing calculator, to look at two polynomial functions and write down some of their key features and behavior. And so for this, you could use Desmos, which is probably the easiest one to use, but I'm going to show it on the TI-84, so you can get a little bit of a experience of how to graph on the TI-84. So we're given this function f of x is equal to 2x cubed plus 3x squared and so on. So I know right now it's positive coefficient and it's x cubed, so it's going to look a little something like this. And maybe there's some behavior in the middle. We don't know yet. And we're also given that there's only this domain that we're interested in. We're only looking at x values from -4 to 2. So on my TI-84, I'm going to go over to my graph input. So I'm going to click y equals. I'm going to type in my function, so 2. The x is right up here, x cubed plus 3x. Oop, that's still up top. So make sure we go over. Plus 3x squared minus 12x plus 4. So that is the function 2x cubed plus 3x squared minus 12x plus 4. When I'm ready for it to graph, I can just go over to this graph button and click graph. So you'll notice I get a picture of my graph, but a lot of it is off the page. So I can set my window manually by clicking this window button and changing my x min and max. That's going to show me the window from x of -10 to +10, y min from -10 to 10. So if we look here, currently our x's and y's are both going from negative to +10. But that doesn't quite capture all the features of our graph we might like. Often if you click zoom and if you go down to zoom fit, now this doesn't always work, but a lot of times that'll sort of capture your function. So this zoom fit here is okay. However, we kind of seem to have lost the sort of max and mins of our function. We might be too zoomed out. So if I zoom in a little bit more, right? Yeah, so this scale doesn't look so good. So we're going to put in a manual scale. Let's say our x min goes from negative. Well, on our function that we given, it says we want the domain -4 to +2. Okay, x SCL means the scale, so we're counting by ones. Then y min, y max. Let's try -50 to +100. We might need to change that. Okay, so we get a decent look at our graph. I think our y's are too big, so let's go back to window. We'll change our y's. Let's maybe make it -25 and +40. You kind of just play around with it. Sometimes if you really look at the function, you might be able to figure out what you need. But that looks good. That's the slice of the function we want to see on this domain from -4 to +2. So we played around, we zoomed in, we got our function. Okay, so now we want some information about this function. So the first one is domain. Typically the domain of a cubic is all real numbers. However, we've chosen to restrict it to -4, 2 for whatever reason. Okay, the range of the function on this domain. So we want to know what's the max and minimum values on this window here. So you could use your graph here, and I suppose we will for the max and maybe for this min here, but honestly it would be easier to plug in -4 because that's clearly the minimum. But let's try this. So one of the ways we can calculate maxes and mins and relative extremas is this calc button, which is above trace. So we're going to hit second and then calc. And if I want the maximum value, I'm going to scroll down and click enter. I'm going to go towards where I think it is. And you'll notice it says left bound right here. So you want to pick somewhere you think is to the left of it. Then it'll ask right bound, so you'll pick somewhere to the right of it. And then we're going to click towards the middle. Okay, so it says we have a maximum at x equals -2 and y is 24. So our range seems to be 24 as the upper piece. And note that that is actually only giving you the relative maximum there. I could do this again, calc and say minimum, and I could go over to our minimum, or our relative minimum, click enter. On the left bound, click enter where it seems like the right bound, and then take my best guess. And we're getting a minimum at y equals -3. But we can clearly see the function goes below that. That's not the absolute minimum of the function, that's the relative minimum. So actually, I'm going to write this down now, though. For extrema, we have the coordinates 1, -3, so that's a relative min at 1, -3. I forget what the x coordinate was of our max, so if we go back to calc and we say max again, and then we scoot on over, I remember the y coordinate was 24, but we missed the x. It's looking like it's going to be -2, and it is, so x is -2. So On our domain that we've chosen, this is an absolute max. On the function itself, it's a relative max. I'm just going to write max at -2, 24. So if we're really intent on only caring about this domain, that's an absolute max. If we actually want to consider the entire function 2x cubed plus 3x squared, I mean, that's going to be a relative max. So I'm just going to write max because this is sort of just an exercise. We don't have a really good reason to care one way or another. And then this last one, I'm going to try to get this minimum value down here, which probably won't actually work. Instead, if I know it's going to be when my window ends here at -4, I can actually go to this table feature. So I'm going to go to second table. And if I want to think about where is x -4, I can just scroll to that. And I can see y is -28. So that is going to be my range is going to be -28 to +24, both inclusive. So I'm using all these kind of different tools. I've got the calc button, I've got my window, I've got table, I've got graph. And so I can analyze this function in many different ways using this TI-84, which is pretty handy. And yes, you can do this on Desmos also, but it's nice to be able to do it in this handheld calculator. Okay, now we want some intercepts. So again, this calc button is going to allow us to find the intercepts of this function. So if I go to calc, these zeros are the intercepts of the function. So if I scroll over to where I think the 0 is, and I press enter, left bound, press enter, right bound, and then go enter where my guess is. I have a 0 at -3.423336. It's probably an approximation, so I'm just going to say our x int, one of them is going to be at approximately -3.42, 0. Then let's calculate. Looks like we have 2 more over here. So we're going to go second calc, 0. I'm going to scroll on over. So we go left bound, right bound, and right where we guess. So this time we have 0.37. Again, that's probably an approximation. So we're just going to roll with it, but we'll say 0.38, 0. Okay, and then our last one, we'll go second calc, 0, scroll on over, left bound, right bound, and go for it. Again, that's probably an approximation. It's probably a irrational number. So we're just going to go 1.55, 0. So there are x-intercepts. If we want the y-intercept, we could try to sort of trace over it, but I think the table is going to be easier. We can say, oh, what's 0 for x? Well, we get 4 for y. So that's pretty nice. So then we get y-intercept at 0, 4. Alrighty. Increasing and decreasing intervals is the last thing that we need. So if we look at our graph, and I'm going to take a little sketch of this graph on our paper now, or on our whatever. We go up, we come back down, we cross through, and we go up again. Oops. Well, we go up, come back down, and go up. Okay. So we look a little something like that. But what we can see then is that we are increasing to this max, then we decrease back towards the min, and then we increase. Again, we're technically bounding ourselves on -4, 2. So we would say we are increasing on the interval -4, we said the x-coordinate of our max was -2. And I choose to say not inclusive there, but it's kind of up to you. And then we are also increasing on the minimum coordinate, which was 1 for our x all the way to 2, which is where our domain ends. And then we are decreasing from that max to that min. So we would say from -2 to +1. Remember, we described those intervals. Those are x intervals. Over what x's are our y's decreasing or increasing? Okay, so that's number one. We're going to look at a second example here. So let's see. Given g of x is equal to x to the fourth minus 3x cubed, so on, and we're curious about it on the interval -1, 5. Now right off the bat, I can see that this is a fourth degree polynomial, so we're probably going to look something like this. That should be a little smoother, maybe like this. So we'll graph it and we'll find out. So let's go over to this TI-84. I'm going to go to y equals, say I wanted to save this polynomial and sort of maybe want to come back to it. I can scroll left to this equal sign and hit enter. So that turns it off, but I can still keep it there, and then I can put my second function. So I can put x to the power of 4 minus 3x to the power of 3 plus 2x squared minus 4x plus 1. Okay, so now I've got two functions, and if I change my mind, I'm like, oh, I need to go back to the other one. It's still there. I would just need to go back to the equal sign and turn it on. So realistically, this isn't going to be in the right window, but let's press graph. Yeah, see, we get a chunk of the function. We can try zoom fit. I always like to see that can sort of help us, but it usually isn't perfect. Yeah, zoom fit, not great here. But okay, if we look at our window at the moment, we're from -4 to +2. I want to just see this whole function. So I'm going to hit -10 to, let's try +10. Try -20 for our y min. Let's just take a peek. Okay, so yeah, that's the general behavior we expected with a fourth degree polynomial. Now we got to get in a little bit closer. So let's restrict our domain to the one the problem specifies. So we want -1 to +5. So that's our x min and x max. And then our x scale will just count by ones again. Y min, it seems like we don't go that low on the y's. So let's try -10. And then our y max, we kind of have to play around in estimate. So let's try 50. And we'll graph it. Okay, not bad. I would kind of like to see the features a little more clearly. I'll probably get plenty of information. If I go down a little bit more, let's try y max of 20. Okay, let's even try 10. We seem like, okay, so we're kind of getting the general idea of things. We can even bring this y min in a little bit, try -7, y max, let's even make 7. Okay, -8. Okay, so it really seems like we only have one max or min on our domain here. Notice that the function runs off our page based on our window, but we'll handle that later. So okay, domain, technically the domain is really all real numbers for this function, but we're choosing to only care about the domain of -1 to +5. So we'll put that in our inclusive brackets. Our range for this function, so it seems like our minimum is going to be here. So that's going to get us some of our extreme values. So let's get that while we're at this. So extreme values, we have that seems like the absolute min of the function in general anyways. Min at, and so let's use our second calc. Gonna go min. And okay, it seems like it just locked onto it, which is kind of nice. But there we go. So 2.0004, -7. My guess is it's actually 2, -7. So if we go to our table, if we go to 2, we get -7. So sometimes the calc, if you don't tell it exactly in the right spot, it'll be slightly off. So you kind of have to make a judgment call. But yeah, so we have a min at 2, -7. Our range then, our minimum value is going to be -7 inclusive. Then we'd like to know how high this goes on that interval. So remember our domain is -1 to +5. So if I go to my table, at -1 we are at 11. So that's the y coordinate on this far left, even though it's off the screen. So that's 11. At +5, we are all the way up at 281. If I were to set my window to 281 on the y-max, we should expect that to be in the top right corner, and it is. Okay, that makes our rest of the graph a little weird to look at, but we can say when our x value is 5, our y value is 281, so that is our maximum. And I'm just going to call it a max at 5,285. I mean, again, technically that's not really an extrema, but because we've cut off our domain, like, it kind of is. Like, that's our max value of this graph. So that's a little bit weird. But okay, intercepts. Okay, let's look at the table right now. We can see our y-intercept when x is 0, our y is 1. So our y-int, we can say, is 0, 1. There's nothing obvious for an x-intercept, right? I don't see any clear y values. So we're going to go back to our window. We're going to fix this y-max. Let's put it at like 8 or something. Back to our graph. So we've got 2 x-intercepts. So let's go second calc. Those are the zeros of the function. And we'll go over, we want to take a left guess, take a right guess, and take a official guess. So we get a 0. I mean, again, it's an approximation this time, but our x-intercept, we're going to call it 2.75, 0. And then let's look for our second one, second calc, 0, and go on over, press enter, go to the right, press enter, take our guess. Okay, and so we're calling this 0, 0.27. Okay, again, those x-intercepts are going to be irrational inputs, so we get our best decimal approximation and just say it's good. Okay, increasing and decreasing intervals, so let's sketch the function now. And it really shoots off here. So we come down, we have our little minimum, we scoot back up and sort of scoot off. It's not a great sketch, but we can kind of see the function sure looks like it's always decreasing. All right, let's do that in a different color. Until our minimum, and then it looks like it's always increasing after our minimum. And there is this little, you can click this trace button and kind of go through here. There's this little curviness to it. So it's like, is there anything there if we check a scale? Not really as far as we can tell, like maybe, but you kind of want to use calculus to really know for sure. So for our purposes, we're just going to say it's decreasing. So we are say our intervals, remember those are x intervals, increasing / decreasing. So we're going to say increasing from that maximum to, so coordinates are max are 5 to the end of our domain. Oh wait, not our maximum, our minimum. So 2 to 5, and then we are decreasing from -1 to 2. And this is on our domain, that we've chosen up here. Right? Realistically, this function is increasing from 2 to infinity and decreasing from -infinity to 2. Okay. So yeah, that's something to bear in mind. Okay, great. So that is sort of how you can use this TI-84 graphing calculator. It has lots of really great features: table, calc, windows, graph. You can store functions. You can even plot multiple functions at the same time. So if I go over here and hit enter on the equal sign. Now these are both turned on. So if I go to graph, you can see them both. You could even look at where these two intersect. So if I go to second calc, is intersect, and then you go and scoot over, you take a left guess, take a right guess, take a guess, and it says it intersects at 1, -3. If we go to our tables now include both of these functions. If I go over to 1, I can see -3. So that's a really handy feature also. You can use that to solve equations using the graphing calculator. So it's really, really nice. Awesome.